We present graph-based robot global localization informing situational graphs with architectural graphs. Our research focuses on providing situational awareness capabilities to robots, towards which we have developed a hierarchical environmental modeling algorithm. In this paper, we investigate on how the hierarchical models of the environment can be used in construction sites. Today I will present our system architecture in detail and the results we have achieved, and how we will extend and improve this work in future. Here we present an overview of our approach. We generate an offline architectural graph or A graph from the BIM model. Our robot then estimates an online situational graph or S graph from its sensors. We do graph matching between the two graphs, align them, and then merge their information. This generates the final informed S graph or IS graph, which is utilized by the robot to be localized with respect to the BIM. Situational graph or S graph is a jointly optimizable 4-layered vector graph. The first layer is the keyframe layers with robot pose estimates. The second layer consists of the wall surfaces, which represents the wall of the environment. The third layer contains the room of the environments, and the final layer is the floor layer, which gathers all the room within a given floor level. The front end of situational graph consists of multiple modules. A 3D LiDAR filtering module filters the incoming raw LiDAR scans. A robot odometry module estimates the robot odometry either from LiDAR measurements or from the robot encoders. Plane segmentation module segments the plane from the LiDAR scans at each keyframe. Room segmentation module first generates free space clusters, and then using such clusters along with the mapped planes, it detects the room centers. Flow segmentation module utilizes the information of all the currently mapped walls to extract the center of the current floor level. Loop closure module utilizes a scan matching algorithm to recognize revisited places and correct the drift. Finally, the back end generates the 4-layered optimizable graph with suitable constraints. Architectural graphs are created from the information extracted from the BIM model. Architectural graph has two layers, a topological layer and a matrix semantic layer. Topological layer has two factors, room factor and a doorway factor. A doorway factor constrains two rooms to each other. In matrix semantic layer, we also have two factors, a wall factor and a wall surface factor. A wall factor constrains two surfaces of the same wall to each other. Once the A graph is generated and the robot starts to generate an online S graph, the incoming S graph is matched with the entire A graph using our novel graph matching algorithm. The rooms of the A graph and the S graph and their subsequent planes are matched to each other based on their geometry. Once a geometrically consistent solution is found, the robot uses this information to perform global localization. Here we show the demonstration of our proposed approach. Once a unique geometrically consistent match is found, we merge the A graph and S graph together. Here we assume A graph is the ground truth. Therefore, while merging the two graphs together, we merge them in such a way that the error between the walls of A graph and the walls of S graph is 0. Similarly, the error between the room of the A graph and the room of the S graph is 0. And that is how we perform the global localization of the robot. We achieve state-of-the-art result both in real experiment as well as simulated experiments. In the future, we will incorporate the inconsistencies and deviations between A graph and S graph and improve our localization algorithm. Moreover, we will add multi-floor and multi-session capabilities to our system as well. Thank you for listening.